Hello, I'm Samantha Christoforetti. I'm an astronaut on board of the International Space Station, where I have been living, working, and conducting research for several months now. I would like to introduce to you today different objects with different masses. One is me, and then I'd like to show you these two baseball balls. They're absolutely identical. They're very precious, belong to my crewmate Terry, and he was kind enough to let me borrow them. This ball, which is somewhat similar in size, a little bit smaller, but as we will see later, has a much smaller mass, and a knitting needle. And all those objects, including me, appear to float. We often say that all objects are weightless in space, but that does not mean that there is no gravity. Let's take a look at this equation. This equation allows us to determine the gravitational pull on the surface of a planet. So let's see, we have big G. Big G is a constant, often referred to as Newton's constant, although actually it was determined 70 years after Isaac Newton's death by Harry Cavendish. Then we have big M. Big M is the mass of the Earth in kilograms. So that would be around 6 million kilograms. And big R is the average radius of the Earth in meters. That is about 6,370,000 meters. Introducing numbers, we determine small g as being equal to 9.81, and that can be expressed in newtons per kilogram, and it basically represents the amount of weight per kilogram of an object in that particular point in the gravitational field. Or we can also express it, and that's equivalent, as meters per square seconds, and that is the acceleration of a free-falling object in the gravitational field. You can make your own calculations for the International Space Station. Just add to the radius of the Earth the altitude of the ISS above the surface of the Earth, which is about 400,000 meters. If we do that, we get a value for small g roughly equal to 8.7. So on the surface of the Earth, we had 9.81, which is about 10% bigger. So the force of gravity, the pull of gravity here up on the International Space Station is indeed a little bit smaller, but not that much. So if there is the force of gravity up here, why am I floating? To explain that, we have to introduce the concept of free fall. So let's use this model of the Earth. And let's enlist the help of a friend, Paxi. You might know her. Paxi, hello Paxi. She's with me on the International Space Station. So for the purpose of our little demonstration, let's assume that Paxi is the space station. We have calculated a short time ago that the gravitational pull of the Earth up here at 400 kilometers altitude is only about 10% smaller than it is on Earth. So if the Earth is attracting us, why don't we, Paxi, me, the entire space station, why don't we just crash onto the Earth? Well, the thing is that we also have a huge velocity vector. We are flying at about 8 kilometers per second. And that means that if there wasn't the gravitational pull of the Earth, we would just keep going straight at that velocity. However, because the Earth does attract us, the Earth curves our trajectory so that we keep flying around it. In a way, we can say that our trajectory, the curvature of our trajectory, matches the curvature of the Earth. So Paxi, me, the space station, we are all constantly falling towards Earth. But in a way, the surface of the Earth is curving away from us so that we never crash onto it. Objects of different mass, like let's say me and the knitting needle, are accelerated equally in a gravitational field in the absence of air resistance. This was demonstrated nicely on the Moon in 1971 when Apollo 15 Commander David Scott dropped a feather and a hammer on the Moon, and they were both equally accelerated towards the center of the Moon and hit the surface at the same time. Also, if we could set up a controlled experiment and had a long time to observe, we would notice that all objects with mass are attracted to each other. This knitting needle to me and me to the knitting needle. How long do you think, roughly, it would take for these two objects to come together due to their gravitational attraction? So, despite objects in free fall being weightless, their mass does have an effect. That effect is called inertia. Inertia is the property of objects to continue in their existing state of rest or uniform motion in a straight line unless their state is changed by an external force. And mass is a measure of an object's inertia. So let's see what the effects of inertia will be if we put these objects together. These three objects are now linked together and they act as one system. Let's say I decide to push down, and I push down on one of the baseballs. The system translates down, but it also starts to rotate. And it rotates around its center of mass. It's like the balance point of the system. And in this case, it's the middle point, because these are equal baseballs. So let's say I push down on the center of mass. In that case, the whole system translates down, but it does not start to rotate. The center of mass is also called barycenter. And an example of a system like this among cosmic objects is the asteroid pair 90 Antiope. Now let's see what happens if we replace one of these baseballs with the ball I introduced to you earlier today. And I told you that it has a smaller mass. And I can feel that because I can feel that it has a smaller inertia. But you can't feel it. So I want to show it to you. So we'll attach it in place of the baseball. Okay, now we have a new system, a system that is not symmetric, because the baseball is more massive than this white ball. How can we see that? Well, let's say that I want to push down, and I'm going to push down on this lighter white ball. It still rotates, but you probably noticed it does not rotate anymore around the geometrical center. This is not the center of mass anymore. In fact, let me try and push down on the geometrical center like we've done before. I induce a rotation, because that is not the center of mass in this case. So let's see if we can find the center of mass of this system. Just by looking at the way it rotated, I would say it's probably around here. Pretty close. Examples of such systems in cosmic objects are, for example, the Pluto-Charon system, but also our Earth-Moon system. And in that case, the center of mass is about 1,700 kilometers beneath the surface of the Earth. So while these objects are weightless, and I am weightless, mass still exists, and it causes many interesting physical phenomena that make space research and science so fascinating. So I really hope you enjoyed watching this little demonstration. And the next time you watch the International Space Station flying over our head, think of the astronauts up there, constantly falling.